Our last talk is from Matan Ben Sion from Exact Sciences.
So my name is Matan. I'm from the School of Physics and Astronomy. Today I'll talk about a potential new way of treating I'll just use this. Can you hear this? Excellent. Today I'll talk about potentially a new way of developing antiviral drug treatments. I'm going to start actually with thermodynamics. I'm going to think about viruses very differently than what most of the time you think about viruses as particles, spherical particles. This is what physicists do. And hopefully I'll persuade you that thinking about them thermodynamically in this regard may develop a new strategy for antiviral treatment. I have a couple of disclaimers. Unlike previous speakers, I will use equations. I'll try to make them succinct, but equations and math are my sharpest scalpel. And I think it may be illuminating why this approach is useful. I also show some experiments, not with viruses, except for those that I did at home. So this is more personal. I was sick in the past 2 weeks. So I did some experiments with viruses, and it took me a very long time to recover until today. Yeah. I hope this is not false positive, false negative. I'm not sure which one of you is scary, which one of these is scarier for you. But let's start, and let's start with a simple example, which maybe you're familiar with. Short DNA oligos don't bind well at room temperature. So if you take a short strand, 8 nucleotides long, and mix it in a solution with its complement, perfect complement, high GC content, you may expect it to hybridize, to make a double helix, the DNA double helix. But what ends up happening is most of them actually don't hybridize. The melting temperature of such a short strand is very low, something like 4 Celsius. So at room temperature, it's melted, let alone in physiological temperatures. And this can be actually calculated and predicted from a very nice model from about 20 years ago, using the standard enthalpy and entropy for this reaction, given the concentration that the strands are in. Now you can do a trick, and you can graft particles, nanoparticles, or microparticles, colloidal particles with DNA. So you make these fuzzy particles, and they have a plume over here of the DNA. So they're sticky particles, and then you can mix these in solution with their complementary particles that have complementary DNA. And this is what it looks like under the microscope. They do bind. These are short sequences. At room temperature, they shouldn't bind. But once you put them on particles, they actually do aggregate spontaneously and very strongly. Moreover, you find that the melting temperature of these aggregates is much higher. It's 45 Celsius instead of 4 Celsius. Now, usually when you're developing drugs, you don't think about melting temperature. You think about concentrations or effective concentrations. And from this relations, you can actually translate what are the effective concentrations. But let me give you some intuition, mathematical intuition. What's behind this effect? And it's actually the most intuitive way to think about it is think about it as a Velcro effect. You have many weak bonds, but you have many of them. So you can write the partition function for the single-stranded DNA in free solution, and it has 2 states. One, which for the unbound, or this Boltzmann factor for the bound state. From this, you can calculate the melting temperature. But once you graph these strands on particles, the partition function becomes the product of all these bonds that are formed. So this product adds up to this power of number of bonds. Which means that now the melting temperature, the association temperature of these 2 particles is much higher because of this N, because of the number of bonds participating. This means that for very weak bonds, the thermal fluctuations would normally break. Once they're grafted and they work together, they will bind even at room temperature or physiological temperatures. What does this have to do with viruses? So first, let me translate this equation into a more physiological context or a therapeutical context, so you can recast this in concentrations means that at a given temperature and given salt concentrations, etc., this is what the concentration for effective binding is. It means that it decreases exponentially. And if you want to design a drug, it means that you'll need an exponentially lower dosage of that drug. So it will have much less side effects. Even if whatever molecule you design doesn't have perfect matching to the epitope you're after. Okay, now what would this look like on virions? Let's say you take this guy. We've all seen this one two years ago, the mugshot. If you see this on the street, run away. When I saw this, I thought, oh, this is a nanoparticle with fuzzy sticky ends on it. If you try to bind directly, let's say making short peptides or some repurposed drugs that can have some finite binding, you may get some binding, but it won't be great. Most of the molecules will be unbound. But if you instead graft, say, a polymer or a larger particle, it's a polymeric carrier with these binding sites, even if these binding sites are very weak, you can get very effective binding, very effective sequestering. For those of you who are familiar with chelating, this is a little bit like EDTA, chelating of metal ions, which is very strong and can sequester metal ions from a solution because it has multiple bonds to the atomic orbitals of the metal. But unlike a metal or atoms, viruses are not that quantum mechanical, so you can still have many other bonds. So what is more likely to happen is that you'll get this. You'll get clusters, you get what's known as agglutination, which is great because if you make large clusters, and large clusters being instead of 100 nanometers, maybe half a micron, you can trigger the innate immune system. So even if you haven't developed a vaccination or got a vaccination, you can treat the effects of the viruses, especially where their concentration is high, where the viral load is high. And and then macrophages, for example, can take over, and viruses themselves are too small for macrophages to see. But once you have clusters, half micron pathogens, macrophages can have higher effectiveness of phagocytosis, even if they're not specific. So I promised experiments not just with myself. So we did that. We started with, we created model particles and we agglutinated them. We also made a control of dispersed suspension of particles. These were 200 nanometers particles. We mixed them in solution and we introduced them to macrophages from a cell line of mice. And we actually saw that there was over an order of magnitude increased cytosis of the agglutinated particles. In other numbers, you can say that almost 100% of the agglutinated particles went into the macrophages. The dispersed particles went in something like 3% of them. So it was much more effective to introduce for the cytosis to happen this way. And this was done in collaboration with Mary Goldschmidt, which helped me a lot. Who helped me a lot with macrophages from Dan Pear's lab. So to summarize, a polymeric multivalent carrier may be a general platform for antiviral drug development. You can put on such a carrier different molecules, peptides, repurposed drugs, etc. Perhaps this will be something new. Like we discussed earlier, maybe we need something new. This may be a very useful technique. And the outlook, something about the future, we need to do this more systematically, have some more quantitative controls that I'm looking forward to do. I'm also looking forward to go beyond concept and working with actual viruses. There are some world-leading virologists here who can work with alpha virus, rhinovirus, something that is not too severe, not too pathogenic, and try to see if it actually works with actual viruses. And I'll be happy to discuss this with you. I should thank my sponsors, the Center for Combating Pandemics, the lab of Yael Khini in the Condensed Matter Department, Misrad Aliyah Vaklita for returning scientist, and Paralab who helped with the macrophages. And I'll take questions.